So this is going to be the newest stuff. If you decide on becoming an engineer, fluids is an important subject, but it's also important if you're going to go into, let's say, something like biomedical engineering or even medicine. You know, you think about fluids, your body's got blood in there. It's got all these fluids going around in your veins. There's pressure and all those other things. So there's a lot of physics behind all that. The goal for today is I'm going to give you some easy problems, and then by the end, we're going to look at a more difficult problem. Okay? So this is going to be the build-up, and we're just going to take it step by step by step. So after you get the first step down, the second step isn't going to be that much more complicated, and it's not going to be more complicated. And by the end, you'll look at a complicated picture, but it'll make a lot of sense to you, hopefully. That's the idea here. So we've got a pipe here. This is just a little bit of the pipe, and there's water flowing through it. It's a tube, maybe. I don't know, whatever you want to call it. And so we got water flowing through there. Now, the first thing you want to know about water is that it's not compressible. You can't compress water. So if you push water, let's say 2 gallons this way, and you've got a whole bunch of water everywhere else, then somewhere else 2 gallons of water has to be pushed because you can't compress the water. So if I push this way, then this part of the water is also going to get pushed by some amount. And I'm not talking about the speed, although the speed could be the same, but the amount of water. So if there was like 15 gallons here that got moved, then somewhere right here, 15 gallons also has to move. That's the idea, okay? So here we have a picture, and the speed of the water is 4 meters per second. So the water is flowing at a speed of 4 meters per second. And what we want to do is find the fluid flow rate. Now, the fluid flow rate is the volume, the change in the volume divided by the change in time. So when we talk about the fluid flow rate, when you see this word, what they're really talking about is dV dt. Now, I didn't mess this up on purpose. I'm writing the V like this, so that way you don't get it confused with velocity. So that's volume, and that's velocity. All right? So we want to know what dV dt is. And we've got water flowing in this direction right here. So let's start with dV. dV is the change in the volume. The volume is going to be the cross-sectional area, this thing. And if you look along this pipe here, it's not difficult to see that the area here and the area here and the area here doesn't change. So we leave that term alone. But volume is length times width times height. We just have the surface area. We need to move it by some displacement dx. Like so. So A times dx will give you dV, an incremental change in the volume. Okay? So hopefully that's nothing too difficult to understand. If we were just looking for volume, it would be A times x, but we're looking for the incremental change in the volume. So that's going to be dV is equal to A dx. And our goal is to figure out what the flow rate is. So what I have to do is I have to divide both sides by dt. Now from here, you get the idea of what's happening. dV, volume, dt, is going to equal the area. Hold on a second. Hey, good news on me. Okay, so we got dV dt. Here we've got the area, and dx over dt is just the velocity v. Okay, and here's the thing. Well, we could solve for it now, and then we'll talk about the other thing. We know what the area is, and we know what the speed of the water flowing in this direction is. So we just plug it in. we would get area, which is equal to pi r squared multiplied by the velocity, which is 4 meters per second. And so r is equal to half of this, so 0.05 meters. You plug that into there, and you will get 0.0314 cubic meters per second, because that's volume and that's time. So you get cubic meters per second. And so that's what the flow rate is going to be. And this shouldn't be that bad. This is pretty easy to understand, that the volume over the time is just equal to the area times the velocity. Okay, hopefully that was pretty straightforward. Something that caught my attention was that we have dv over dt is equal to a times v. If I look at a point here, or if I look at a point here, the area is exactly the same, which means that the volume will be exactly the same. The velocity will be exactly the same. But we'll get back to this in just a second, why that's so important. No matter where you are, I'll repeat this, and I'll repeat again later. No matter where you are, dv dt is going to be the same amount. However many gallons you push this way is going to be the amount of gallons or whatever volume that you're pushing this way. It won't change. It doesn't matter if this gets wider or smaller. The amount of volume that's being pushed out per time is going to be exactly the same no matter where you are. And that's going to be key later on. Now, let's just check to see if this actually works out. So we're moving at 4 meters per second. And let's see how much volume do we actually get this volume here. So if we're moving at 4 meters per second, the amount of volume on a cylinder, if we drew it out, in 1 second, the length of this would be 4 meters. Hopefully you agree with that, because you're moving at 4 meters per second. So it's going to carve out 4 meters in the cylinder. That's how much water got pushed out in 1 second. And we can use the equation volume is equal to the area, cross-sectional area, times the length. And so if we multiply the area, which is pi r squared, by the length, which is 4 meters, you end up with 0.0314 meters cubed. So that's how much the rate was, and that's how much we actually get after 1 second. Okay? That's a quick way to check. Now, following this, let's look at another example, except now the tube is going to be of different size. So you have a tube that's going to decrease like that. Whoa. That's not so bad. I'm pretty impressed with myself. And so this is D1. And this will be D2. And what can we know from this? What do we know from this situation right here? You've got water that's being like squeezed into this little area right here, and it's all going to get pushed out that way. Here's the thing. The amount of volume that's being changed over time here, is going to be exactly the same amount of volume that's going to get pushed out there. So if I were to make a drawing of this, we could say, like, let's say this is how much volume got pushed out after 1 second here. But if you compare it to here, it would look something like this. And that's how much volume gets pushed out there. So this is thinner, but it's much wider. Here it's thin right here, but it's wider in this aspect right there. Hey, Helen. So the amount of volume over time that gets pushed here is going to be exactly the same as the amount of volume that gets pushed out here. And that's true no matter what the fluid is. And this is kind of super important. So even if you squeeze your pipe, the amount of volume that's getting pushed out over time is going to be identical to the amount of volume that's getting pushed out over here. Why is that important? Because over here, our equation, we already said, was the area, the cross-sectional area, times the velocity. Over here, it's going to be the cross-sectional area times the velocity. And hopefully you understand from here, these two right there, that the area at this point is going to be different than the cross-sectional area at that point. And if this and this are equal, these two have to equal. And so if A1 is not equal to A2, then V1 can't equal V2. But what you do end up with is this equation right here. A1 times V1, so that's the area of this times the velocity of this, is equal to the area of that times the velocity of that. And all of that is going to equal dV dt. And dV dt here is exactly the same here, which is exactly the same there. So if dV dt is the same throughout any portion of this, we can say that dV dt has to equal a constant. Constant. All right. And know this, because we're going to go back to it. No matter what the problem is, this is going to hold true, that the area, the cross-sectional area times the velocity of 1 is going to equal the area 2 times the velocity 2. And from here, we could do a simple problem where we could say D1, let's actually work it out. Let's do one and see. Although you kind of get the idea just from the equation, it's kind of nice to actually write it out. Let's say that D1 is equal to 10 centimeters. And D2 is equal to, let's do 20 centimeters here. So 20 centimeters here, 10 centimeters here, D2 equals 10 centimeters there. And we've got a velocity of D2 of 4 meters per second. So D2 right here, D2 is equal to 4 meters per second. And just from this, without even doing any sort of calculations, you should know, like just from looking at this, even just from like using a hose, when you change the cross-sectional area, the water shoots out really fast. So here the water is shooting out really fast, which implies that the water here has to be shooting out really slow. And we are asked to find V1. So we can, use our equation right here. What's V1 going to equal? V1 is just going to be equal to A2 divided by A1 times V2. And so here you have A2, which is this point right here. So let's actually write it out. Pi r squared, pi. Well, we don't even have to do that. We could just do 10 over 20. And I'll tell you why. The radius and the diameter are proportional. So it's just a factor of 2. They get multiplied out. So you're just going to be left with 10 over 2. And then the pi r squared, the pi term cancels out as well. So you'll just be left with 10 over 20. And you don't even care about the units because they'll cancel out. And you get half. So it'll be 1/2 times A1. What is it? Not A1. V2, which was 4 meters per second. And so velocity 1 is equal to 1/2 4 meters per second. So velocity 1 is going to equal 2 meters per second. Okay, that should be hopefully a pretty straightforward question. All we're doing is changing the cross-sectional area, and this is what we get. Keep that in mind because we're going to go back to this. So understand this. This is probably the simplest question you can get. We're just comparing this. And when will this equation not be true? Never. You can always use this equation. So remember that. You can always use this equation if the cross-sectional area is going to be changing. And if the cross-sectional area changes, that means that the volume will, the speed will change. Okay. So now that we've done that, let's talk about my guy, Bernoulli. Bernoulli's equation. So Bernoulli's equation is a very important equation in fluid dynamics. It's something that you're probably just going to have to memorize at some point. And I'm going to derive it for you later. But for now, I'm just going to give you the equation and we're going to work it out. On Friday, we'll actually derive it, okay? So what is Bernoulli's equation? It is that the pressure, P, the pressure in the fluid, plus the density of the fluid times GH, which is gravity, times the height, plus 1/2 the density times the velocity squared is equal to a constant. Star. Remember this equation right here. So that's Bernoulli's equation. I'll repeat it one more time. It is the pressure in the fluid plus the density times gravity times the height. Height. That's the key. What this is saying is now we're not moving like this. The water isn't flowing in a straight direction. It's going to go something like this and go up. Or it could go like this and change down. Because now there's going to be a height factor involved. And because it's a constant, what that means is that whatever is happening here, whatever Bernoulli's equation is over on this height right here, is going to be equal to Bernoulli's equation at this height right here. That's what the word constant means in this context. So let's look at our problem and we will work some stuff out. So let's go from down to up. So we got a pipe here. It's going to go down and then go up. Ooh, I don't have Akane's drawing skills, but I think I got, oh, no. Almost. Yeah. That's pretty good. That's pretty good. So we're going to look at a point right here, and we're going to look at a point right here, and we will call this P1, so pressure 1. And over here, this is equal to pressure 2. So far, so good. We're going to have a speed V1 here, and we're going to have a speed V2 here. And anything else? Let's say this is ground. So this will be, thank you, Akane, thank you, 10 out of 10. So this height right here will be H1, and this height right here will be H2. So that's everything that we got here. Here's the situation here. If the height changes, so I'll let you take a second to draw it out. Go ahead and draw this out. Okay, so hopefully you've drawn that out. And I'm going to compare my two Bernoulli equations. Bernoulli's equation here has to equal the Bernoulli equation there. So the way I'm going to do it is I'm going to first look at this term right here, and that's going to give me the pressure at 1. Density of water doesn't change, or whatever fluid it is. Gravity doesn't change, but we have height 1 here, and we're going to have velocity 1 here. And that's going to equal Bernoulli's equation over here. So whatever this is, I can write here for this term right here. So we're going to have pressure 1, or pressure 2 now, plus the density, which doesn't change, the gravity doesn't change, but the height does change. It becomes height 2 plus 1/2 rho V2 squared. So that is our Bernoulli equation. In a nutshell, this is what we've got so far. The pressure and the volume and all that stuff is equal to the stuff here. I want you to take a second to just look at this equation and really get a feel for what's happening. What we've done is changed H. You can see that from here. I've gone from H1 to H2. So this part of the equation has changed. If this part of the equation, if this term right here has changed, that means something else has to change too. Just like when we did area times velocity equals area times velocity, if the area decreases, the velocity increases for something else. It's the same thing over here. We're changing H1 to H2. And so what can change? Well, the pressure could change. That's one thing. So the pressure at 1 could be different than the pressure at 2. That's one thing that could happen. Something else that could happen is the velocity could change, because that's also in this equation. The density of water doesn't change, or whatever fluid it is. It's going to stay constant. So the velocity could change. The two things that could happen here is that because you've changed the height, the pressure has changed and the velocity has changed. Okay? Now, in this problem, let's go back and remember what we had said about the velocity. Do I have it here? Here we go. If the volume over time is constant, right? No, sorry. Did I erase it? I did erase it. We had said that dV, the volume, over dt is equal to a constant, which means that A1 V1 is equal to A2 times V2. And so I'm going to go back to this equation first, and I'm going to look at that picture here. If you look at this picture here, as the water flows from here going up into here, the area, the cross-sectional area, didn't change. I don't care about the height. I'm just looking at the cross-sectional area that the water is flowing through. So if the cross-sectional area doesn't change, that means that A1 is equal to A2. And therefore, if A1 is equal to A2, then V1 has to equal V2. So the velocity of the water that's flowing down here is going to equal the velocity of the water over there. And that's because the cross-sectional area doesn't change. Okay? Why is that important? Well, that makes our problem significantly easier now, this Bernoulli equation, because we just said that the volume at 1, because A1 is equal to A2, volume 1 is going to equal volume 2, which is just equal to V. And so this term right here and this term right here are exactly the same, and they get canceled out. You can subtract one from each side. And so now we're left with this equation right there. So what's this equation telling us? It's telling us that the change in the height, the changing of the height, will result in a change in pressure. Now, okay, we got that. I'm hoping we got that. Predict what you think would happen to the pressure just from, common sense. When you go up in elevation, what should happen to the pressure in something? And so you don't have to write down, just think about it and have an idea of what you think would happen as you go up in height. Does the volume increase or decrease? And we'll do an example. So let's let H1 equal 5 meters. H2 is going to equal 10 meters. What else? The velocity, V1, V2, we said was exactly the same, so we don't care. The velocity of this fluid that's flowing is equal to 2 meters per second. But in our problem, it doesn't even matter, huh? Pressure 1 is equal to 2 ATMs, atmospheric pressure. And we're talking about water. So the density of water is equal to 1,000 kilograms per meter cubed. So that's the density of water. And what we want to know is what is the pressure at the second height. So what's the pressure over there? If it's 2 ATMs over here, what's the pressure over there going to be? Is it going to be bigger than the pressure at 1? Is it going to be less than the pressure at 1? What will happen? If we go to our equation here and we solve for pressure 2, we just have to bring this term to the other side, and we will end up with pressure 2 is equal to P1 times rho G, and then we have H1 minus H2. All right. And then we can start plugging our values in. What do we want to write this in? Let's see here. We'll put everything in terms of ATM. So 1 ATM one atmospheric unit is equal to 1.013 times 10 to the power, I want to get this right, 5? Yeah, 5 newtons per meter squared. So that's the atmospheric pressure. Force divided by the area, so that's what pressure, the units of pressure are. Another way of saying this is Pascal, P, capital P, lowercase a. So 1 ATM is equal to that. And we want that because we want everything in terms of ATMs in this case. So when we plug everything in, we have 2 ATMs plus the density of water. The density of water is 1,000 kilogram over meter cubed times gravity, which is 9.8 meters per second squared. And then we multiply this together. Now H1 is less than H2. Already you should understand what that means, what that implies. If H1 is less than H2, this is going to be a negative number. So when you take a positive number and you subtract from it, pressure 2 is going to be less than pressure 1, just from this equation right here. But we could plug it in and see. So H1 is equal to 5, and H2 is equal to 10. And so when we do that, we're going to end up with 2 ATM plus all of this multiplied together is 4,900. 4,000, oops, minus sign, 4,900 newtons per meter squared. And we want it in terms of ATM. So I'm going to take this and multiply it. What do we want? 1 ATM on the top. And on the bottom, we're going to have this number right there. 1.013 times 10 to the power 5 newtons per meter squared. And the newtons per meter squared cancel out. And you just multiply across. And you will end up with pressure 2, P2, is equal to 1.52 ATM. So you went from having a pressure of 2 atmospheres to 1.52 as you went up this pipe right here. And I'm just going to quickly recap what we did because it's important to understand why we can get away with doing this. The first thing is you use Bernoulli's equation. Because it's constant, it's equal to a constant, you can say the equation here has to equal the equation there. The next thing we did was we looked at the cross-sectional area here and we compared it to over here. Now the cross-sectional area here and here were the same. If the cross-sectional area is the same, then the speed in which the water flows is going to be the same. So then we got rid of that, and then we're left with this equation right there, and we're good to go. So that's how you do Bernoulli's equation for this. Now to end it, the last thing we'll do, just because I know this is where we're going, is what happens when the area, the cross-sectional areas aren't the same. So we're going to take the idea that we learned from the first example, and we're going to put it into the second example, and we're going to put everything together as one equation, okay? So let's do that. We'll do it over here. Let's see here. So we're going to start off big, and we'll go smaller like that. And so it's going to start off wide, and then it's going to get thin at this point right there. Okay? And so here we have H1. You can't see that. At this height right here, it's going to be H1 equals 0. And then we can keep going. And this will be H2. And H2 is going to equal 5 meters. Okay? Or you could also look at this as delta H now if you want, because that's what it is. We're not interested in like what this height and like somewhere below is. We're just interested in the difference in the height between where the water flows here and where the water flows there. And what else can we say? We can say that the cross-sectional area, here is 0.2 meters squared. So A1 equals 0.2 meters squared. And the cross-sectional area here, A2, is equal to 0.1 meter squared. So we got the cross-sectional areas there. What else? Let's use a different color here. We'll say that the velocity at the bottom, is equal to 4 meters per second. So V1 equals 4 meters per second. And the last thing is the pressure. So the pressure, P1, is equal to 2 atmospheres. So the pressure is equal to 2 ATM. And what I want to know is what is V2, and I want to know what the pressure at that height is also going to be. Did I miss anything? I think that should be everything. Oh, and this is water still. So the density of water is 1,000 kilograms per meter cubed. So that's the density of water. So you got water going here, and it's going to get pushed up there. And what we want to know is what the volume at 2 is and what the pressure at 2 is. Okay? So let's do that. Take a second, and you write it out, and I'm going to write it out as well. All right. So while you're working it out, I'm going to write down Bernoulli's equation, and we'll go from there. So we've got P1 plus rho G H1 plus 1/2 rho V1 squared, and that's equal to P2 plus rho G H2 plus 1/2 rho V2 squared. So there's our Bernoulli equation. And what we want to do is solve for V2 and P2. So what I'll do is I'm going to solve for P2. We'll worry about V2 in just a second. So if I solve for P2, we will get that the pressure on 2 is going to equal the pressure on 1 plus, you bring this to the other side, the rho and G are the same, and we'll get H1 minus H2. And then we'll bring this term to the other side where 1/2 rho is constant, and we'll get plus 1/2 rho. And on the inside would be V1 squared minus V2 squared. All right. And even before we do any sort of analytics or any sort of math here, just appreciate this equation and try to understand what it's telling you. This is our starting pressure, right? Let's say if we start off with a large pressure. If this thing is negative, if this term is negative, our pressure will decrease. If this term is negative, our pressure will decrease. So how would you get this first term? How would you get this first term to be negative? How would you get the first term to be negative? Would be is if H2 is bigger than H1, right? If H2 is bigger than H1, this is a negative number. So if that's true, then we are going to have, therefore, pressure 2 will be lower. So P2 will be lower than P1. Just from that. That should be pretty straightforward to understand why that's true. If you take some number and subtract from it some negative thing, if you do any negative to it, this value would get less. So as you go up in elevation, if H2 is higher in elevation than H1, the pressure will go down. We knew that already. We talked about that before. But what about the velocity? Because the velocity is something else that's interesting. So let's look at the velocity, and we do the same game that we did there. So over here, if velocity 2 is greater than velocity 1, in other words, if the speed increases, because velocity 2 is the second speed. So if the second speed increases, if you're moving faster than you were in the beginning, well, pressure will go down. That's what that's saying. So if you go up in elevation, the pressure will go down. If you start to speed up, if the water starts to flow faster through the tube, the pressure will also go down. So those are the two things. Increasing the height will decrease the pressure. Increasing the speed will decrease the pressure. Those are our two things that we want to look at. Okay? So this one we can deal with right away. How do we know what the velocities are? Well, we just use our equation. A1 times V1 is equal to A2 times V2. That's the very first equation we learned. And that will tell us the velocity. We don't need Bernoulli's equation to tell us the velocity, which is why I put it in terms of P2 here. I'm solving for P2 in this Bernoulli equation because the velocities we can solve from our very first equation. Okay, so let's do that over here. You get because d times the volume over dt is constant, as always, that's going to be true. Constant, that's kind of hard to write from here. Then we get that A1 V1 is equal to A2 V2. And if we solve for V2 here by plugging in A1, A2, and V1, we will end up with 8 meters per second. So the volume here is 8 meters per second. That's how fast it's moving. Okay, so two things are happening here. This thing is speeding up because it went from 4 to 8. So if it's speeding up, pressure goes down. And the other thing is it's moving up in elevation. So if the height is increasing, pressure goes down. So whatever our answer is, we already know that the pressure 2 has to be less than pressure 1, just by this analysis right here. Okay? Without doing too much math, we've already established that it's not only speeding up, but it's also going up in height. So all we got to do is plug some stuff in. This time, let's put everything in terms of pascals. So let's work it out. So P2 is going to equal 2 ATMs. That was the atmosphere pressure at P1, multiplied by, I'm going to convert it into pascals. So what I have to do is multiply it by 1.013 times 10 to the power 5. Okay, so when you do 2 atmospheres times this, it becomes a pascal, or Newton per meter squared. And then we're going to add to it the density of water, which was 1,000 times gravity, which is 9.8, times H1 minus H2, so that's 0 minus 5. And then I'm running out of space, so I'll write it down here, plus 1/2 the pressure, the density, which is 1,000, and then V1 minus V2. So V1 is equal to 4. So we got to do 4 squared. It's 16. 16 minus V2, which was 8, right? So 8 squared is 64. And then we just solve for P2. The pressure is going to equal, P2 is equal to 129,600 pascal. So that's P2. Well, what was P, or we'll call it Newton meter because that's what you're used to seeing, Newton per meter squared. So what was P1? P1 was just this number right here. It was 2 times this. So that's going to be 202 something like that. So 2 times this is going to give us that, 000 Newton per meter squared. So we went from a very high pressure to a lower pressure, and that's what we thought we would get using our equation right there. And so that is Bernoulli's equation. That is the first lesson on fluids. I think that should be more than enough for today. Hopefully you got something out of that. Hopefully you understand how to use this equation. It looks like a lot, but it's actually not. If you followed what I said from the beginning of this lesson until like this part right here, Friday's lesson isn't going to be as bad either. We're going to actually derive this equation on Friday. So be on the lookout for that. Other than that, we are done for today. Hopefully your brain learned something.